Alright, so I wanted to talk about a couple different scenarios, and I'll probably do this over the course of a few different videos because I want to work out some problems. But we got to talk about what happens in finding the pH of different acid solutions. The first type would be a strong acid, and strong acids completely ionize. So they're the easy one. Since strong acids completely ionize, that means the hydronium concentration of the strong acid solution will be equal to the strong acid concentration itself. So in this case down here, you have 0.1 molar HCl, so that means essentially you have 0.1 molar hydronium. So take the negative log of that and you'll get a pH of 1. That's all you have to do for strong acids. Now, if you have more than one strong acid mixed together, all you got to do is add their concentrations together and you will end up with the overall hydronium concentration. You can take the negative log of that. So not that difficult. Weak acids, though, are a little bit more difficult because they do not ionize completely. So this is where equilibrium comes into play. So, for instance, I have as an example here, hydrocyanic acid. You have a 0.1 molar solution of hydrocyanic acid. So what we do is we say, well, first of all, we need our balanced equation. Let me go ahead and let's say HCN plus H2O, which is the pure liquid. The rest of them are aqueous, so we won't include the water. Then you'll have cyanide and hydronium, okay? So when we're making our ice table, we'll have HCN, Cn minus, and H3O plus, ICE, like that. Sorry, I probably should have drawn out my ice table before I started the video, but... So we have 0.1 molar hydrocyanic acid. Nothing over here. So minus X plus X plus X, 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 0.1 minus X there. Now, on the acid table, you can see that hydrocyanic acid has a Ka value of 4.9 times 10 to the negative 10th. So we set this up. We say X squared's on top, 0.100 minus X is on the bottom. Now, just work it out like normal. In this case, we can use the X is small approximation because there's more than 3 powers of 10 difference between the starting concentration and the K value. So we'll say this is going to be 0, which means 4.9 times 10 to the negative 11th is equal to X squared. Then we take the square root of 4.9 times 10 to the negative 11th, and we get 7.0 times 10 to the negative 6 equals X. So we've solved for X, and in this case, X is actually equal to the hydronium concentration at equilibrium. This doesn't always happen, as we'll see later, but in this case it does. So if I take the negative log of 7 times 10 to the negative 6th, oops, I didn't even put log in there, negative log, sorry. That's going to be the pH. So in this case, negative log of 7 times 10 to the negative 6th is 5.15 because there's 2 sig figs here. So 5.15 gives me 2 sig figs behind the decimal point. So that's how you do it if you're trying to find the pH. This case, sorry, I should have commented on this. I went all the way through because I don't want to do some of the other examples to take more time on this video, but this one just asks for the hydronium concentration, so this is the answer. But from here on out, a lot of times it's going to ask for pH instead, so that's what you would do for pH. Anyway, we will talk next about mixtures of acids, but this is how you would do a weak acid by itself.